Hey, Armathea. Hey, Armathea, how you doing?
I'm good.
Good. Is there something I can do for you?
I think I took the wrong test on Tuesday. I think I took 17, not 16.
You shouldn't have been able. Are you okay? Yeah.
Yes.
All right. You shouldn't have been able to do that. But
That's
let me go and check and see what's going on right now anyway, okay?
okay.
What was it about?
17 was Lewis laws or something.
Yeah.
Yeah. I took it already and I didn't take 16. I was supposed to take 16. But some way I got to take 17, not 16.
Okay. Let me look in here. I swear to God, I fixed this. All right. Oh no, you should have taken Lewis Dot today. 17 is what you 17 is what you should have taken.
Yeah, I took it Tuesday though, instead of today.
Okay.
Because I thought I was taking 16, but I actually took 17.
Okay. Yeah, well, this is the one that you had to do for today.
Yeah.
So that's how I misunderstood you.
Yeah.
Okay, I'll let you take it. I will let you take 16. 16 is the hard one.
Oh Lord.
Yeah, I know it's a hard one. It's the questions the gas law questions.
Oh Lord.
Sorry.
It's hard. Period. I tried to learn that thing. It's hard.
Um, yeah, I know what you're talking about, Armethea. It seems like there's 10 million equations, and you got to kind of shuffle through them all, right?
Yes, I'm trying to learn it, but I don't know. It's like when I try to do like one equation that goes with that, then I think I was doing the wrong one.
Have you taken this quiz yet?
No,
The reason I need to ask that because if you have, I need to give you another attempt.
no, I haven't taken it off. But I
Okay,
thought I was
so
taking 17. I
okay.
thought I was taking 16, but I took 17.
If I give you till tomorrow at 5, is that enough time?
Yes, sir.
Okay, just do it slow. Do it
Yeah.
slow and try and understand which formula you need to use. Okay?
Okay. So I have a question though about that
You should,
P1
one,
and
se- one
P2
sec,
thing.
1 second, okay? I just need to get back to where I was. Okay. Let's go for it. The
Okay.
P1 and P2 thing.
Yeah. So when you're doing that question, do you use the molecular weight or the molar weight? I don't know the
Okay,
difference.
hold on a second. Molecular weight and molar weight are the same thing.
They're the same thing or not the same thing?
Yeah, swear to God. Swear to God. But are we talking about the gas laws?
Yeah.
I'm sorry, yes or no, Armithia? I didn't understand you.
Yes.
Okay, gas laws don't usually have molecular weight in them.
Oh, okay.
P stands for pressure.
Oh, okay.
All right, let me I'm gonna share screen. Good. All right. Are you seeing the screen, Armithia?
Yes.
All right, let's see if we can help. Let's see if we can help with this. All right. Do you see these equations here, Armethea?
Yes.
All right. Now, what you have to do is you have to look at the problem.
Mm-hmm.
And you have to look at the problem and you have to figure out what's staying the same and what's changing.
Okay.
And based upon that, you're going to use either one of these four formulas
Mm-hmm.
or you're going to use this formula. Okay, Armethea?
Okay.
If nothing changes,
Mm-hmm.
the parameters aren't changing, pressures aren't changing, volumes, if none of those are changing, you're
Mm-hmm.
using this formula.
Okay. Nothing
All right.
changed with that.
All right. Now understand when I have PV equals nRT,
Mm-hmm.
I've got a pressure, I've got a volume.
Mm-hmm.
N stands for moles.
Okay.
T stands for temperature. Okay. And R is a constant. A constant's a number that doesn't change.
Okay.
All right. And if my pressure is in atmospheres, my volume is in liters,
Mm-hmm.
N is in moles, and T is in Kelvin, then
Mm-hmm.
my R has a value of 0.08206.
Okay.
Does that make sense to you?
Yes.
All right. Now, if things are changing, what
Mm-hmm.
you have to do is you have to look and you kind of like have to say, okay, you got to keep everything that is changing.
Okay.
Okay. Kind of like put a line in the middle of your paper and say, okay, this is changing, this is not, and this is not.
Okay.
Okay. So when you have something like that, you got to figure out what's changing and what is not.
Okay.
So we're going to go and pick a problem out at. All right, let's look at this problem, Armethea.
Okay.
Okay. Is anything changing?
The volume.
Volume's changing. Okay. So if something's changing, are we using PV equal nRT?
No.
So that one's out of the question. All right. Now, okay, if you look at the very bottom line of this, okay, it's saying temperature doesn't vary. So already you've said volume is changing, right?
Yes.
And what does the question say about the temperature?
Temperature. It doesn't vary, so it doesn't change either.
So it doesn't change. So right now, of our four parameters, you know that the volume is on the side that's changing,
Mm-hmm.
temperature is on the side that doesn't change. Okay.
Okay.
Now, all right, it says assume that the gasoline was immediately combusted.
Mm-hmm.
All right. If it's immediately combusted, have I made all the particles I can make?
Yes.
Am I putting any more particles in there?
Can't because it's limited, right?
Well, no, just right here. Does it say I'm putting any more in?
No.
Am I taking any out?
No.
So this is particles or moles, right?
No.
So are the moles changing?
No.
So moles are not changing. So I got two things. Temperature and moles are not changing.
Okay.
I've already know that volume is changing.
Mm-hmm.
Okay. Now that implies if I have two parameters that aren't changing and one that is, that means that fourth parameter has to change too.
Yeah.
So I've got volume and pressure that are changing. I've got moles and temperature that are not.
Mm-hmm.
So what I've got to do is I've got to pick out a formula. I've got to pick out a formula that doesn't have N or T in it, but does have P and V in it.
Boils.
Boyle's law. So that means I've got my pressure times my volume under one conditions is going to be equal to my pressure times my volume at another condition.
Mhm.
So I got to find that problem again. And there it is. Okay. So now, Armethea,
Mhm.
which pressure goes with which volume?
It's 6.45 with the 4.26, right?
Okay. Is that what it says, though? Read the problem carefully, Armethea.
Okay. Oh, the 6.4 with the 135.
All right. That's why you got to be careful. Remember, I said at one point, you got to be careful that you keep the conditions
Together.
that are the same parameters together. Okay. So if
Okay.
the 6.45 and the 135 are together, they go on one side of the equal side. The 426 goes on the other.
Okay.
So I have my law here. I just simply put 6.45 times 135 is equal to my second pressure times my second volume.
Then you divide it by the 426.
Yeah, yes. You multiply 6.45 by 135, divide by 426.
Okay. I got it now.
Okay, that's just one though. That's just one. I've got another problem here. Okay, Armethea?
Okay.
All right. Now, tell me if anything's changing first.
Um the inflating the maximum volume of the balloon.
So is the volume changing?
No,
The
because
volume's
it's
not
already
changing.
it's maximum volume. Um no. The volume's not changing, the moles
It's
are
not
not
changing. What's right now? Right now, what is the volume at?
3.35 liters.
What does can be inflated mean to you? Does it mean it's happened, or does that
Oh,
mean it can happen?
it can happen. It hasn't happened.
So are the conditions, are the volume, is the volume of 3.35 right now?
No,
No, it's not at 3 point. What is it at right now?
2.76 liters.
Mm-hmm. And what are the number of moles at the 2.76 liters?
2.83 liters.
2.83. Okay. Now, what the problem is saying is that if you want to burst it, you got to put more air in it to get it to this level, right?
Oh,
So you want
so,
to take it. So you do want to change the volume. The volume is going from
so
2.76 to 3.35.
the volume is changing. And the
And
moles got to change, right, to get
the
the
goal
volume
moles
there.
got to change. So those are both on the change side.
Yeah.
Okay. Now, are we at sea level? Did we move from sea level?
Is there at sea level and room temperature?
It's at room temperature and sea level. So are we changing the temperature?
No, or the
Are,
sea, or no,
or the
or the
sea level? Sea level implies pressure.
pressure. Yeah.
Okay. So pressure and temperature are not changing.
Okay.
Moles and volume is.
So I use
So
one with the V in the end.
absolutely. Okay. And when you go to do your test,
Mm-hmm.
I want you to copy these formulas on a piece of paper.
Okay.
All right. So if my V and N are changing and my temperature and my pressure are not,
Mm-hmm.
which one of these formulas am I using?
Avogadro's.
Avogadro's. Okay. Is this, again, Armithia, the math is not that hard. The hard part is understanding which of these formulas you need to use.
Is figuring out which one to use.
Mm-hmm. That's all. That is the hard part. By the way, hi, Faith. Hi, Jennifer. Do you have any questions?
Nope.
Okay.
Now, yeah.
No problem. Armithia, I want you to try one more.
Okay.
All right. Let's look at, sorry, 1 second. Okay, we're going to look at this one. Okay. What volume is occupied by 11 grams of carbon at 25 C and 371 torr? Armithia, is anything changing?
No.
Nothing's changing. So which law do we use?
The RNT, the RNT.
Yep, absolutely. PV equal nRT. And that is called the ideal gas law. Now, we got to figure out how to make the stuff we need to solve it for PV equal nRT. Because
Yeah.
remember I said, Armithia,
Mm-hmm.
that if I want to use this number for R, I got to change the pressure to atmospheres, the volume to liters, the temperature to Kelvin, and the moles to moles. Okay. So let's do the temperature first.
Okay.
I need to change from C into K. Do you know how I do that?
Is the 25 plus the 370. Let's see. 373. I mean
Nope.
273.
273. Good, good, good. 25 plus 273 is 298K. So we got one of our values. Okay. I have 371 torr.
Mm-hmm.
I need to get to atmospheres.
Go
ahead. Do you remember what the number is?
No, I think it's I don't remember.
No problem. For every 1 atmosphere, there are 760 torr.
Okay.
So if I'm starting off with 371 torr and I want to get atmospheres,
Mm-hmm.
1 atmosphere for 760 torr. Does the atmosphere go on top or does the torr go on top?
The tour.
If I put the torr on top, I'm starting with 371 torr. I'm going to be
Mhm.
multiplying it by 760 torr over 1 atmosphere. Is that
Oh,
going to? So what do I do?
You put the atmosphere on top and the tour on bottom.
I put
Uh-huh.
You're right. I put the 1 atmosphere on top, 760 torr on the bottom. I do that, and I get 0.488 atmospheres.
Okay.
Now, the last thing I have to play with is my 11 grams of carbon dioxide.
Mm-hmm.
How do I go from grams to moles?
You put the 11 grams of and 1 mole over the molecular weight of carbon.
Yes. That thing you were asking me about earlier, the molecular weight or the molar weight, they're both the same thing.
Okay.
So, my carbon dioxide's molecular weight is 44. So I'm going to take it and take my 11 grams times 1 mole over 44. And that's going to give me 0.25. So I have solved my 11 grams for 0.250 moles.
Mm-hmm.
My pressure, I multiplied by 1 atmosphere over 760 to get 0.488 moles. And my temperature, I multiply or added 25 to 273 to get 298. Now all I got to do is plug it into the equation.
Okay.
And I plug it in here and I solve it and I end up with 12.5 liters.
Okay.
Armitha, I want you to come back and talk to me early on Monday as well, or Tuesday as well. Okay.
Okay.
We're going to try and push this through. All right.
All right. Thank you.
Anybody have any questions, ladies and gentlemen? About anything, anywhere? How was the quiz? Was the quiz fairly easy?
Yes.
Oh, come on, Kaylin.
I've just been looking through the lab, and it's it's kind of confusing.
We're going to deal with it. Andrew, we'll deal with it. It's confusing because you're dealing with stoichiometry, you're dealing with gas laws, you're dealing with formulas for a sphere, and you're dealing with limiting reagents. So basically, yes, you're right. There's a whole lot of crap we're dealing with. We'll get through it. All right. There are in many respects, Hunter, I like this lab. In many respects, I don't. It's great because it gives you a visual for what the limiting reagent really is. But there are other problems with this lab that make it problematic for me.
Yeah, I have a crick in my neck too, so it's like it's annoying as hell.
Crack it.
I'm afraid I'm just gonna I'll just like die if I crack it.
Bottom line, if I don't crack, basically when the pressure goes crazy, my neck goes crazy. And if I don't figure out a way of cracking it, I got to go take a muscle relaxant. So I'm with you. I feel for you. Okay, ladies and gentlemen. Ladies and gentlemen, we are going to deal with something called Lewis dot structures. Okay. We're dealing with something called Lewis dot structures. And basically, this guy, Lewis, perfect philosophy. If I don't have to deal with it, I'm not going to deal with it. The inner electrons, I don't need to know they don't do it. They're not involved in bonding. Why do I care about the inner electrons? I'm only going to draw the valence electrons. And because they're the only ones involved in bonding, if I draw the valence electrons, that's going to tell me a whole lot of information that I need to know about. So, by the way, for those of you that are tired of math, the next couple lessons we're dealing strictly with non-math stuff.
Oh, I can remember I can remember all sorts of facts and stuff, so that's great.
All right, so as I said, the guy Lewis decided because the chemical properties are directly related to only the valence electrons, those are the only ones I'm going to draw. And you draw them very specifically. Valence electrons, there are going to be 8 of them.
Professor,
At the most.
I'm sorry to interrupt. Are you trying to show us another PowerPoint? Because we still see the other one.
I was just trying to make sure if you were paying attention.
Ha ha ha.
All right. They haven't shown you anything of value yet. Okay. When you are drawing the electrons around an atom, you draw them singly. You draw 4 of them in the 4 sides. Then you pair them up. So if I'm drawing oxygen, all right, oxygen has 6 valence electrons. So I am going to start around. I'm going to draw this one, this one, this one, this one. Then I'm going to pair up one of my electrons. I'm going to pair up another one. Now, do you remember way back when we were talking about covalent bonds? What does it take 2 atoms to bond with one another?
They have to share
Share what?
valence electrons.
They have to, each of them has to give at least one electrons to make a bond, correct? Everybody remember that way back when I was talking silliness. Remember all that? If you don't, remember it now. In order for two atoms to form a bond, each one of them needs to donate an electron. Okay, let's look at oxygen. Already we have some information about it. How many unpaired electrons does oxygen have?
2.
So how many things can bond to oxygen?
2.
2. All right. Let's draw nitrogen. Nitrogen has 5 valence electrons. So I'm going to put them down 1, 2, 3, 4. I'm going to pair one of them up for the 5th electron. How many free electrons does nitrogen have?
3.
Any argument, ladies and gentlemen? So if it has 3 unpaired electrons, how many things can bond to nitrogen?
3.
Carbon?
4.
4 of them.
4 valence electrons, 4 unpaired electrons. There are 4 things that can bond around carbon. Again,
How many for hydrogen?
how many? Okay, how many electrons can hydrogen have around it? It's at the top of the periodic table.
1.
Just 1.
Hydrogen has 1 electron. It can have a maximum of 2. It's the only one you have to worry about. All the rest are 8. So because hydrogen can only have 2 electrons, hydrogen can only have 1 thing bonded to it. We good with that?
So what about all the other diatomic elements?
Okay. All right, the diatomic elements, all right. I have oxygen, right? You're gonna
Yeah,
have to bear with me. You're gonna have to bear with me, Rosina, because I can't really draw this too well. Well, maybe I can.
I guess it wouldn't apply in oxygen's case because we always do H2O2 and such, but
No.
oxygen.
Oxygen is O2, right?
Yeah,
So if I'm making a bond, if I'm making a diatomic of oxygen, this is what I'm doing. Nope. Okay, Rosina,
got it. Yeah,
what happens? I've got 1 oxygen has 2 free electrons. The other oxygen has 2 free electrons. So what happens is each of the oxygens donates 2 electrons. So I have a double bond between the oxygens
got it.
with 2 lone pairs over here and 2 over here, 2 over here, 2 over here. Okay, Rosina?
Got it. Thank you.
All right, so how many dots are around sodium?
Just one?
Just 1. All you got to do is look and find how many valence electrons sodium has. It only has 1. So we are only going to bond 1 thing to it. How about phosphorus?
5.
5. So literally speaking, phosphorus is going to look like nitrogen. How many things can bond around phosphorus?
3.
3. Because phosphorus would be just like this only instead of N, I would be putting P there. Okay? Now, in just the same way, I can represent molecules. Just like I did with the oxygen, I can do the same thing with other chemicals to represent where the electrons are coming from and where there is a bond between the atoms. So if you remember, my carbon had 4 unpaired electrons. Each hydrogen has 1 unpaired electron. So if they share, if hydrogen shares its electron and carbon shares its, then I get a bond between carbon and hydrogen. But I've got 3 more carbon electrons here. Another one can come over here, another one over here, and another one can come over here. So I can now use my Lewis dot structures to represent molecules. Is this kind of making sense, guys? Anybody confused? Hunter, I'm hoping that pained expression comes from the crick in your neck.
Well, I was thinking earlier in the semester, and some of the homeworks, we were like connecting these Lewis dot structures, if I'm right, or maybe there was some other exercise I was working on, but I just remember we were using those in like the first 2 homeworks or something.
I remember that. That was in the very beginning when it was teaching us how to use the system.
Yeah, remember that?
Okay. No, I'll trust you. I'll trust you on that. That basically they have, in order for them to get you to be able to draw things within the homework that's coming up, they have to expose you to it. So yes, you are going to be doing that in the homework for mastering coming up. Okay. Is anybody not understanding the basic concept behind representing molecules in this fashion?
No, I get it. Pretty much.
Throwing it open, guys. I'm hearing crickets. Come on, if you're not understanding this, let me know. Because I'm going, the next slide, we're going to get into the rules. And I'm going to need you to write these rules down.
Professor.
Yes, sir.
So all of those hydrogen molecules are bonded with 2 electrons each, making 2, 4, 6, 8 total electrons, right?
Yes. Now, if you want to think about this, hydrogen's happy because it's got 2 electrons it's sharing through the bond, each one of these hydrogens. And carbon's happy because it has 8 total electrons that it's sharing around it. Both the hydrogen and the carbons are very, very happy right now. Are we good, guys?
By happy,
okay.
Stable, right?
Stable. Yes. Okay, there are a series of about 10 rules. You're going to be given a molecular formula. What I want you to do is write the atoms down on the piece of paper. You want to put your least electronegative element in the center. So if I have something like silicon dioxide, oxygen is much more electronegative than silicon is. So I have silicon and I have 2 oxygens on the other side of it. Write the elements down, put the least electronegative one in the center. Add up all the valence electrons. You need to account for the charges of ions. Okay? Each element is going to have an amount of valence electrons. You have to add up all the valence electrons from the individual elements within the compound. Then if it's an ion, you either have to add electrons if it's a negative charge, or you have to subtract electrons if it is a positive charge. So if I have something like SO4 2 minus, I have to account for that. Sulfur has 6. Each oxygen has 6, but there are 4 oxygen atoms. So I have to multiply that 6 by 4. My charge is 2 minus. So I have 2 from my extra electrons. I add these all up. I get 6 times 4 is 24, plus 6, 30, plus another 2, I have 32. If I have NH4, one plus, I have my nitrogen, 5. I have 4 hydrogens. Each of them have 1. Now I have to subtract 1 out because I have a plus charge. 5 plus 4 is 9 minus 1. This is equal to 8. First step, again, we are going to write the atoms down from the chemical formula. We're going to put the least electronegative in the center. Next step, add all the valence electrons.
Professor, where are you getting like the numbers from? I don't understand how you're.
All right, do you have your periodic table out, Chase?
I do.
All right, now count over from the left. Do you see where sulfur is? Look just below oxygen.
Yes.
All right, now with your one finger on the sulfur, I want you to count the boxes over from the left and tell me how many you have.
What am I counting to? Like
You
all
can-
the way
you-
over?
All right, you're counting from sodium over to sulfur. Each box counts 1.
1, 2, 3, 4. 5.
No. So
Am I-
sodium, right? Sodium counts 1. Okay, I gotta sit there and think. Not calcium. Magnesium. All right, sodium's 1. Magnesium is 2. Aluminum is 3.
Oh, so 6.
6. That's where the 6 is coming from. Chase, remember a long time ago, I told you to put above hydrogen 1.
Mhm.
Put above beryllium 2.
Okay.
Put above boron 3, carbon 4, nitrogen 5, oxygen 6, fluorine 7, and helium 8 or 8. Yes. Helium only has 2, but everything below that has 8.
But why are you counting from sulfur to sodium?
Why am I counting from sodium over? Because each time I add an element, I add an electron, don't I?
Mm-hmm.
So if I'm going from, if I start with, all right, everything from, I'm trying to think how best to explain this, Chase. All right, do you see where neon is?
Or what?
Neon, Ne. Inert gases, second one down from helium. Chase?
I'm trying to find it. You said it was Ne?
Ne, neon, right below helium.
Oh, I see it.
Okay, now, whenever you have an inert gas, this means that all of the inside electrons, all of the orbitals are filled with electrons. And I have to go out and make a new shell. Does that make sense, Jace?
Okay, so to find that number, I'd count from Ne over to lithium.
No, no, Chase. Neon has a completely filled set of orbitals, okay? In order to add another electron for our next atom, we have to go to a new orbital. Each time we add a new orbital, we have new valence electrons. Valence electrons are the outermost electrons. The reason they're important is they're the ones involved in bonding.
Okay.
Guys, we're going to have to go over this.
Yeah.
We're going to have to go over this at a later time, okay? I got to get through some material. Are you in lab tonight?
I'm not.
Okay. We'll come in early next Tuesday, okay?
Okay.
Anybody else not understand where I'm coming up with the valence electron number? All right, so I've counted all my valence electrons. Next rule, I have to put 2 electrons between each of the elements. The 2 electrons between the elements mean that there's a bond, mean that it's part of the molecule. I subtract the amount of electrons I used in bonding from the total amount of electrons. Then I fill my terminal atoms with pairs of electrons. So if my terminal atom is attached to the center atom, 2 electrons are already present in that terminal atom because they're being shared with the center atom. I want a total of 8 electrons around that terminal atom. So I have to put 6 more around that terminal atom. The way we put them around the terminal atom is in terms of pairs that are called lone pairs. So rules 5, 4, 5, and 6. I put 2 electrons between the terminal atoms and the center atoms. These 2 electrons are bonding electrons. And I need to have them there because if I don't, then it's not bonded in the molecule. I count up all of the bonding electrons I have and subtract it from the total valence electrons. Next step, I fill all of my terminal atoms with pairs of electrons. If I have 1 pair of bonding electrons, that attaches that terminal to the center atom, it has space for 6 more. They get put around the terminal atom in terms of 3 pairs. Questions so far? Now, in step 5, I subtracted the bonding electrons from the total number of valence electrons. In step 7, I'm going to add up all the lone pair electrons I have and subtract that from the remaining electrons. If I have any leftover electrons, they go on the center atom. Now I look at my center atom and I count and I see how many electrons are around my center atom. Remember, I've just put any leftover electrons into the center atom, so I have no more electrons left. If the center atom does not have 8, I have to steal a pair from the terminal electron. I do that by taking one of the lone pairs off of the terminal atom, put it between the terminal atom and the center atom. I've just made a double bond. Last, I got to see that every atom has 8 electrons around it. A note here, guys. All of the halogens have how many valence electrons around them?
None.
How many electrons? The halogens, fluorine all the way down. How many valence electrons?
None.
What?
7.
7.
7. They have 7 valence electrons around them. Guys, are you having troubles counting valence electrons? Tell
No.
me, is anybody other than Chase having trouble with valence electrons? All right. Now, how many valence electrons does fluorine and all the other halogens below it have?
7.
They have 7. So, if I can only have 8, how many things can be bonded to the halogens? How many?
1.
There's only 1 unpaired electron, so only 1 thing can be bonded to the halogens. That stops the molecular chain right there because the halogens can only bond to 1 thing. Similarly, hydrogen has only 1 electron. It can only accept 1 more electron. It also ends any molecular chain. So I'm going to work this with you, or pretty much I'm going to do it by myself. I've got my formula, SeO2. I'm going to write my atoms on the piece of paper. I'm going to put the selenium, because it's the least electronegative, it goes in the center. Rule number 3, I have to put 2 electrons between the left oxygen and the selenium. Oh, before I do that, I have to count the valence electrons. How many valence electrons does oxygen have?
8
6.
or 6, sorry. 6.
6. How about selenium?
6.
6.
So, total number of valence electrons, 6 plus 6 plus 6,
18.
18. So I've got 18 valence electrons. First thing I have to do to put the electrons in, I have to put 2 between the left oxygen and selenium. I have to put 2 between the right oxygen and selenium. So it looks something like that. I started with 18. How many did I use in my formula already?
4,
4.
So 18 minus 4 is,
14,
I got 14 left. My next rule says I put them in pairs around my terminal atoms. The two oxygens are my terminals. So I put 2, 4, 6 around that oxygen. I put 2, 4, 6 around that oxygen. Two, 4, 6, 2, 4, 6. How many more have I just used? Count them. 2, 4, 6, 8,
12.
10,
Well,
12.
Does it matter where we put the dots when we're drawing them out? Like I know that you have to put it around, but does it matter if we start on the top, the side, or the bottom?
You mean start? No, not really. Not
Okay.
really, because you're going to put the dots around there until you fill up the terminal with 8.
Okay.
All right. So I had 14 left. I just used 12 of them. That gives me how many remaining electrons?
2.
2.
The 2 extra ones go around the center atom. I've used up all my electrons. I got 2, 4, 6, 8 around that oxygen. I got 2, 4, 6, 8 around the left oxygen. But looky here, selenium only has 6. I don't have any more electrons, so I got to steal them. I got to take 2 of the electrons from the terminal atom and I got to shove them in between the oxygen and the selenium and make a double bond. So when I make the double bond, selenium now has 8. This oxygen has 2, 4, 6 lone pairs, 1 bonding for 8. This oxygen has 2, 4 bonding plus 2, 4 lone pairs for 8. My selenium has 2, 4, 6 bonding electrons, 1 lone pair for 8. Everybody's happy. Questions, ladies and gentlemen? Questions about this whole process? Last step was to just check, which we did already. Now, I hate dots. I detest dots. Dots suck. What I do is I represent 2 dots with a single line. It's much easier, it's much neater, and amazingly enough, I don't have to interpret smudges as whether they're dots, whether they're electrons or not. So I would encourage you to do lines. Will I accept dots? Reluctantly. But I'll get back at you in some other fashion. If you can, use lines. So in this particular case, this oxygen has 2 lone pairs. That's represented by the 2 lines that are on the oxygen. This selenium and this oxygen have a double bond. I've got 2 lines between the oxygen and the selenium. The selenium has 1 lone pair, a lone pair, 1 line above the selenium. This oxygen, that should have another line up there. This oxygen has 2, 4, 6 lone pairs, 1 bonding. Questions, ladies and gentlemen? We're going to go through another one. Rules 1 and 2. I've got silicon dioxide. Silicon is the least electronegative, so it goes in the center. Now, let's count the valence electrons. How many valence electrons does silicon have?
4.
1 atom, each one has 4. How about the oxygens?
6.
I'm sorry, did you say the silicon goes in the middle because it has the least amount of valence electrons?
No, Katie, I said it goes in the center because it's the least electronegative atom.
How do you know that?
All right. Do you have your periodic table out?
Yes.
Okay, as you go,
Oh, because it's
Up.
closer to the left.
as you go up and
Yeah.
right, not left, right. Fluorine is the most electronegative. Francinium is the least.
Also, there's color coded
Okay.
things on Google. If you look it up, I printed them out so I can remember it better.
Okay.
Okay, generally speaking, the trend is as you go up, electronegativity increases. As you go to the right, electronegativity increases.
I remember that now. Okay.
It's good that all that training I gave you, Katie, wasn't for naught. So how many, my oxygen, how many valence electrons?
6 times
Times-
2. So you get 12.
So how many total do I have?
16.
Do you all see that? All right, now I've got to attach the oxygens to the silica. So where do the first electrons go in my structure?
On either side of the silicon.
I have to attach my oxygens and my silicons. I attach them by putting 2 electrons between them. So I get a pair of electrons on the left, pair of electrons on the right. How many electrons did I start with? Somebody other than Veronica. I'm sorry, yeah, you, Victoria.
16.
Did I start with 16?
Mm-hmm.
You're right. I started with 16. How many did I use up, Armethea?
4.
So how many do I have left?
12.
12. Got 12 left? Now, anybody remember where I put the electrons next?
On the outside.
Armethea, I think you're going to
Option.
like this section. So yes, I got to put them on the outside. This oxygen only has 1 bonding pair, so we put 2, 4, 6 around it. This oxygen only has 1 bonding pair, so we put 2, 4, 6 around it. 2, 4, 6, 8, 10, 12. I subtract it from my remaining 12. I got none left. Yet, I got none left, but my silicon only has 4 electrons around it. So what do I do?
Create double bonds.
Create double bonds or triple bonds, Rosina. Okay? Double bonds or triple bonds. So if I'm going to make double bonds, one's going to come from here, one's going to come from here. So I'm going to have a double bond with my oxygens each having 2 electrons around, 4 electrons around it. Or I could pull, is there anything that says, that you know of yet? Is there anything that says I can't take both of the electron pairs from one of the oxygens? Is there anything in the Lewis rules that says you can't do that?
No.
So I can draw two different structures. That is something called resonance that we will get into a little bit later. Questions, ladies and gentlemen? Okay. Let's see who's here. I got 25 people here. Alec.
Yes, sir.
Okay, I got 25 people and 5 structures. Alec, Hunter, Apple Grace, Armethea, and Cash. I want you to take a piece of paper and a pen, and I want you to draw the Lewis dot structure for H2O or water.
I'll try.
Chase, Aaron, Faith, Fabiana.
Yes, Professor.
I'm sorry, who just called me?
Did you call my name?
Who's you?
Chase?
Chase, yes.
Okay.
Chase, Aaron, Faith, Fabiana, and Gaith. I want you to do CO2, not SiO2. I want you to do CO2. Hayden, Jennifer, Katie, and Kaylin. I want you to do COS. Leandre, Louis, Marie, Mariah, and Neela. I want you to do CN minus. And go ahead.
So the COS, the O and the S
No,
are
I don't want you to do the CO3 2 minus. I don't want you to do that one.
no COS.
COS, yes.
So the O and the S have the same amount of, they're both 6 and the carbon's 4. So does it matter which goes on the other side, the O or the S, or?
Which goes left and which goes right?
Yeah,
No.
okay.
Okay, last one. And this is going to be Rosina, Victoria, and Zane. Yeah, you guys can handle this. Rosina, Spencer, Victoria, and Zaina. I want you to try to do CO3 2 minus. I'm going to give you about 5 minutes to work on this. And I'm going to give me 5 minutes to actually to write it up.
We're using lines for every two, right? For every pair is one line.
Yeah, or dots.
Okay. But he wants us to use the lines to represent it, I'm pretty sure.
Yeah.
So for water people, I'll put it in the chat.
Okay, 6, 12, 16. Eight. Okay, 6 times 3 is 18, 19, 20, 24. Six, 10, 11. 5, 6, 10. I'm done. Anybody need more time? Okay, this is where I get to see your beautiful faces. I want you to turn your videos on. Turn your videos on. And I want you to display the structure you bought, the structure that you made to the camera. I want the waters to show it first. You're good, Hunter. Okay, Alec. You're missing something, Alec.
Wait, Professor, you said that for every pair we could use one line, right?
Yeah, no, I said, Hunter, I said you were fine. Alec, do you know what you're missing?
Am I
Apple
missing?
Grace? Go ahead, Alec.
Am I missing some electrons?
Yes, you are. Apple Grace, you're good. Anybody I'm missing here?
Me,
Who's me?
Cash.
Cash, I'm not seeing your face anywhere. Ah, gotcha. Cash, you're good. Cash, you're good. All right. Anybody who I didn't call on for the water. All right. Now, the CO2. Those of you I asked to draw CO2, I want your cameras on and I want you to display the structure to the camera.
I think mine's back. Wait, CO2?
CO2. You're correct.
Not
CO2 is
CO3?
correct. You have CO3.
No, okay.
CO2. Who has it? CO2. Faith is good. Aaron, you're missing. Aaron, you're missing the lone pairs around the edge into terminals. Fabiana, you're good. So I got Faith, Fabiana, and Aaron. Anybody else? Faith or Aaron, you want to show it to me again? Chase, I'm not seeing it. Pull it back a little bit. Down, down, down. You're good. No, Chase, no. Okay, Chase, you have too many electrons. First of all, Chase, never put single electrons out there unless you don't have any other choice. So you have 2 single electrons at the bottom of your oxygens, right? The other thing is you have too many electrons. Oxygen and two oxygens and carbon have 16 electrons. If you count the electrons you have there, you have 18. Okay, Chase? So it would be good if you take those 2 single electrons off the bottom away. How about COS? You're good, Jennifer. Hayden, you're good. Kaylin, you're good. Anybody else do COS?
Yes, I did.
Who was I? Who? Katie? Trying to find you, Katie. Yes, you're good, Katie. Anybody else do COS? Okay, how about CN? Neela, are you driving in a car?
No, I'm not.
Tell me, Neela, you're not
I can't
driving
see.
and trying to show this at the
I'm
same
not
time.
driving. Oh, there it is. Okay. No, I'm not driving.
You're good. Neela, you're good. Leandre, you're good. Mariah, you are good. Mariah, show it again. Sorry. Absolutely good. Anybody else do CN? All right, now CO3. I'm sorry. Armithia?
Aya.
Aya. I'm trying to get through here for you. This is not the easiest thing in the world to do. Aya, gotcha, you're good. Now CO3, 2 minus. No, that's CO, no. Victoria, not right.
Oh, did I need
Wrong.
another? I need another oxygen.
You need another oxygen around
Got
there.
it.
Do you see
Anybody else?
Is it right on my screen, Spencer?
I'm sorry, Rosina, show it up again. Spencer, I'll be over there in a second.
Okie dokie.
Okay,
Professor Robbie?
Rosina,
One,
Rosina, on your left oxygen,
Yeah.
do you still have 3 lone pairs around it?
No, I have just 2 pairs. I canceled
Okay.
out one.
Okay. I just wanted to check that. Now, Spencer,
Yes.
do you have CO3?
Yes.
I'm sorry, I'm coming around, trying to find you.
I just hope it's not backwards on my
No,
screen. It is.
Spencer, you're perfect.
Okay, cool.
Anybody else? CO3. All right. I need to tell you one more thing about drawing ions. A lot of you have been doing this before, I could tell, because you knew right away. When you draw an ion, you draw the Lewis dot structure, then you draw brackets around it. Outside the brackets, you put in what the charge is. That's just another little rule that you have to have. Not so bad, is it, guys? Lewis dots, are they that horrible? You're going to need to practice them. I would strongly suggest that you look at the homework, the extra homework that I put into the course folder. I would strongly suggest that you do that and use that, because that is a hand copy that you can look and see whether you have it right. Now, I absolutely want to get through one more thing about Lewis dots before I end tonight. One more thing, hopefully 2. Now, I have 3 possible structures for carbon dioxide. right? Is there any way to say what is the best structure? Yes, there is. There is something that we call formal charge. Now, formal charge is the charge that is on an atom when it is in the atmosphere of the molecule. All right? Formal charge is the charge on the atom when it is within a molecule. Very simple formula to determine formal charge. What you do, the formal charge is equal to the electrons that the atom would have, the normal valence electrons the atom would have if it's just in the periodic table. From that number, you count the number of lone pair electrons around it. A lone pair electron is an electron that it is not sharing with another atom. In other words, it's not a bonding electron. These electrons are completely on the atom and are completely controlled by the atom themselves. They are the lone pairs. Those are the ones that are not between the atoms. So I'm going to take my actual electrons. From that, I'm going to subtract all the lone pair electrons plus the bonding electrons divided by 2. And the reason we're dividing the bonding electrons by 2 is because they're shared between 2 atoms. Formal charge, actual electrons minus the lone pair electrons plus the bonding electrons divided by 2. So let's look. Let's look at my CO2. Okay? If I'm dealing with the first compound, can you see that both oxygens have the same electronic configuration? Each of them has a double bond. Each of them has 2 lone pairs. So they are the same, correct? All right. How many lone pairs? How many lone pairs are around the left oxygen? How many lone pair electrons?
2.
2 pairs. How many electrons, Rosina?
4.
4 lone pair electrons. How many bonding electrons are next to that oxygen?
2.
Each bond has 2 electrons, Rosina.
Right.
How many bonding electrons? If I have 2 bonds and each bond has 2 electrons in it,
4.
how many bonding electrons are there?
4.
All right. So my actual electrons that are surrounding that oxygen, I have 4 lone pairs. I'm going to count all of them. Plus, I have 4 bonding that I'm going to divide by 2 because they're shared. 4 plus 2 is equal to 6. So my formal charge is my valence minus my actual electrons. My formal charge is 0. Okay? Carbon. I have no lone pairs. So the actual electrons I have are due to how many bonding electrons? Guys, how many bonds? How many
4.
bonds? Thank you. There are 4 bonds. How many electrons are in each bond?
8.
There are 2 in each bond, so 4 times 2 is 8. So for carbon in this structure, I've got 8 bonding electrons. They're shared, so they're divided by 2. I have 4 actual electrons around carbon. Normally it has 4. I subtract the 4 that it actually has. It also has a 0 formal charge. So this molecule, this left oxygen, 0 formal charge, carbon 0, this oxygen is 0. If I am dealing with the triple bonds, this is a triple bond, that is a triple bond. If I'm dealing with my carbon, I have a triple bond. How many electrons are from the triple bond?
6.
6. But that carbon also has a single bond.
Total 8.
Total 8. But they're bonding electrons, so I have to divide them by 2. Carbon normally has 4. It has 4 electrons around it. I subtract those 2. My carbon has a 0 formal charge on it. Let's look at the triple bonded oxygen. How many lone pair electrons does the triple bonded oxygen have? 1 pair, how many electrons?
2.
2 electrons. 2 lone pair electrons. How many bonding electrons does it have?
6.
6. So the actual electrons around the triple bonded oxygen are 2 lone pairs plus 6 divided by 2, 2 plus 3. There are only 5 electrons around that oxygen. If I subtract the normal valence, which is 6 minus 5, the formal charge on this oxygen is a +1. Let's look at the other oxygen, the single bonded oxygen. How many lone pair electrons are around it?
6.
6. How many bonding electrons?
2.
So I have 6 lone pair electrons plus 2 bonding electrons divided by 2. There are 7 electrons actually around this oxygen. Therefore, 6 minus 7, the formal charge on this oxygen is a -1. Now, when I want to go for the best structure, a Lewis structure in which all the formal charges are 0 is preferred. Small formal charges are preferred to large ones. And if you have a formal charge, it must be consistent with the electronegativities. These 3 things, these 3 parameters are what you use to judge your structures. Now, based upon these 3 parameters, which one of the structures is better? The one with the 2 double bonds or the one with the triple bond and a single bond?
The 2 double bonds.
2 double bonds, because there's no charge. That is the purpose for the formal charge. The formal charge is to distinguish, when you can distinguish between 2 equal structures, two legitimate Lewis structures, you use the formal charge to tell you which one is the better structure. Let's look at sulfur dioxide. Again, let's deal with the double bonded oxygen. How many lone pairs does it have and how many bonding? Do I have to call on somebody?
4 and 4.
4 and 4. So it has 4 lone pairs and 4 bonding. So this oxygen has 6 actual electrons around it. It normally has 6. So 6 minus 6, the formal charge around this one is 0. All right. Let's look at the sulfur. How many lone pair electrons are around this sulfur?
2.
2 lone pair electrons. How many bonding?
6.
So I've got 2 lone pair electrons plus 6 over 2, or 5 electrons around the sulfur. So if I do that, my sulfur is going to have a +1 charge. Let's look at this oxygen. How many lone pairs are around this oxygen?
6.
How many bonding? And who is answering these? Neela?
No, I'm Kaylin.
Kaylin? Kaylin?
2.
2.
Yes.
Guys, I hope you're trying to answer this at home, because if you're not, this is going to come up in the next test for sure. So we have 6 lone pair electrons, 2 bonding. How many actual electrons are around that oxygen? 6 lone pairs, 2 bonding.
Would it be 6?
6 lone pairs plus 2 over 2.
It'd be 7.
7. 6 lone pairs plus the 2 bonding electrons divided by 2. That is 7. So the oxygen has a -1 charge. Now, if I drew it like this, that's meant to be a lone pair, by the way. Okay. This is meant to be up there. And this is meant to be with that one. If I did the formal charges on this one, this one would be a all right, 1, 2, 3, 4. Sorry. All right. This one would have a formal charge of 0. The middle oxygen would have a 1+, and the sulfur would have a 1 minus. Trust me on it, okay? Now, look at the formal charges here and compare it to these guys, where it was what's the difference of the formal charges for this structure? Look at it right now versus this one.
They're both 0, right?
No, well, the entire thing is 0, but look at the charges on the individual atoms. What is the difference in the charges?
Sulfur is a +1 in the other one, and it's a -1 in this one, so the charges have switched around.
The charges are switched around. Now, which element is more electronegative? Sulfur or oxygen?
Isn't it oxygen?
Oxygen is more electronegative. So which one is going to want to have the negative charge on it?
Oxygen.
Oxygen's more electronegative. It wants to have the negative charge. It doesn't here. It's a positive charge. There is no way you're ever going to get an oxygen next to a sulfur and have the sulfur be the negative charge. That will not happen ever. So it's going to prefer having the sulfur in the center where the sulfur can handle the positive charge better than the oxygen.
I have a question. Where you have the right oxygen has 6 lone pairs plus 2 bonding divided by 2. How did you get 7?
6
Yeah.
plus 2 divided by 2. 6 plus 1.
Oh,
right?
I was doing 8 divided by 2. Okay.
No, it's 6 lone pair electrons plus the bonding and the bonding only divided by 2. Other questions, ladies and gentlemen? It gets convoluted. Believe it or not, this particular molecule has 9 combinations. And even this is not the right one. The carbon should be in the center. So this has 9 combinations. If I was looking at a choice between these 3 structures, here are the formal charges at the very bottom. What is the best structure?
The middle one?
The middle one, because it has the least amount of formal charge. That would go down even further if I put the carbon in the center. Okay, let's do this. All right. Do you remember that we had 2 different ways to draw the carbon dioxide molecule? Do you remember that? We could draw it with 2 double bonds, or we could draw it with a triple bond and a single bond. Does that make sense to you? All right. Now, because we can manipulate double and triple bonds, we create something called resonance. If you are able to make 2 legitimate Lewis dot structures, and they can be, they follow all the rules. If you can draw 2 ones with 2 different organization of double and triple bonds in it, you have something called resonance. Let's look at ozone here. This is the Lewis dot structure for ozone. Is there any reason, is there anything special about the white oxygen that it gets the double bond? Is there anything special about it?
No.
It could just as easily be on the left side, right?
Yes.
So if I could just as easily move this double bond from here to here, I have what's called resonance. And what it does is it makes the structure that much more stable.
So Professor, could you define resonance again?
Resonance is the ability to manipulate double and triple bonds within Lewis structures so that you have two different structures that are legitimate representations of that chemical formula. Sorry, Rosina, it's not nice and succinct.
No, that's a good thing.
Basically, all we're doing is we're manipulating double and triple bonds within the structure. If we can do that legitimately, then we have a legitimate resonance structure. And for right now, I'm not going to get into isotopes. If
So
I
if you-
have, just go ahead.
If you moved the double bond over to the other O, would you have to move the dots of
Yes.
that? Okay,
Yes. Okay. Who's asking the question?
Katie,
Katie. Okay. Do you see these two structures here?
yes.
All right. You see, I moved a double bond down here. This oxygen no longer has 3 sets of dots around it, does it?
No,
They moved over here. So yes,
Okay.
you're absolutely correct.
All right.
There's no reason why this double bond can't be in the up and down position as opposed to the left-right position. If that's the case, then we have something called resonance. My SO2, I have one double bond. It could just as easily be on the right side as the left. That means it exists on both sides. These are equal structures. Therefore, we have resonance. We're done here right now, guys. Questions? Are you
Professor,
Go ahead.
Yeah, I have a question. I'm wondering, we were all good with formulas and equations and whatnot. And why is there a need in chemistry to do it this way through the Lewis dot structure?
Because of what we're doing tomorrow, a couple reasons. One of which is it gives you a sense of what is happening. Unless you did it this way, Rosina, you wouldn't know that SO2 had a double bond. That's the thing you can get directly out of this.
Got it.
The second thing, and probably more important thing, is what we're doing on Tuesday. And that is something called valence shell electron pair repulsion. And it gives you a sense of how these molecules appear in three-dimensional atmosphere. These don't exist on paper like this. They exist in a three-dimensional form. Okay, Rosina? Those
Got
are
it.
2 reasons why we need to do this.
Okay, thank you.
Somebody else have a question? How are we doing with this? Give me a sense.
I'm gonna need more practice with this, but I will
Yeah.
probably do extra work on it just to get the hang of it.
Yeah, I
Well-
agree. I mean, it all makes sense, but like more
Yeah,
practice. always better.
Always.
Yeah.
Always more work. All right. I'm into the court. Are you seeing the screen right now?
Yes.
If I go into course content, legitimately speaking, my lab of mastering has a very horrible homework on this topic. So I would prefer, if you're going to do something, if you're going to do homework, I really would prefer oh yeah, sorry. Let me go here again. This is the normal way you get in here, test 4. Go down to Lewis dots. Check out the extra homework. Lewis practice. It's going to be a PDF document. And what it is it just has the structures here. You're going to be responsible for doing the Lewis dot structures with these particular compounds. And the nice thing is, at the very end, you have an answer sheet. So please, I can't emphasize this enough. Please avail yourself of this homework problem. Do not do SF6. Do not do SF6. Do not do BSF. What those are doing is those are violating the octet rule, and I don't want you to mess with them. So don't do BSF and do not do SF6. You're not responsible for violations of the octet rule. It happens, but you don't need to know about it. For right now, everything that you create should have 8 electrons around it. Anything else, guys?
Professor, one more thing. I noticed that in the solutions here, all the electrons that are not the bonded electrons, they are showing up as dots and the others are showing up as lines. So for us, does it make a difference?
Rosina, when I do it, I do lines for everything, okay? I've seen people do dots for everything. I've seen people do lines for bonds and dots for lone pairs. I've seen people do lines for lone pairs and dots for bonds. Okay? I'm not going to hold you to anything. All I will hold you to is that a line represents two dots or 2 electrons. Each dot represents 1 electron. That's what I hold you to, okay?
Okay, thank you.
Anything else, ladies and gentlemen? Some of you I will see in a half an hour or so.
Bye, Professor.
Bye.
Take care.
Bye.
All right. Thank you.
Take care. Gaith, do I need a picture on you leaving? Gaith, are you having dinner? Gaith, goodbye.